Before we dive in, a quick note. The voices you'll hear in this deep dive are generated by AI. Our goal is to bring you the most valuable insights from the source material in an engaging format, and these AI voices help us do just that.
Hey everyone, have you ever written a line of C++ code, hit compile, and just, well, trusted the magic?
You see the green light, right?
Exactly. The executable appears and off it goes super fast. But have you ever stopped and wondered what's really happening in that split second between your code, the stuff you wrote, and that machine program?
It's a great question. And it's kind of funny because for something so fundamental, it often feels like a black box.
Right.
But the compiler, it's not just some utility you run, it's really the unseen engine driving C++ development.
Yeah.
And the choice you make there, well, it impacts pretty much everything.
Everything. Like what?
Well, think about it. Performance, obviously. Which platforms your code can even run on. Your day-to-day workflow. Even, believe it or not, the kind of bugs you run into.
Wow. Okay. So it's more than just turning code into a .exe file. Absolutely. So, for any programmer who's curious, getting your head around this compiler stuff isn't just tech trivia. It's about actually understanding and controlling your own craft.
Okay, I'm sold. And that's exactly what we're going to do today. We're taking a deep dive into C++ compilers.
Sounds good.
First, we'll unpack why your code even needs this translation step. Then we'll do a quick tour of the main players, the big compilers out there.
The Titans, yeah.
The Titans. And finally, we'll try to give you a clear guide on how to pick the right one for your projects. Hopefully, you'll have some aha moments.
Definitely. Looking at G++ or plel.exe might feel a bit different afterwards.
So let's start right at the beginning, the core problem. Why does our nice C++ code, with all its std.counts and loops, why does it need a translator at all?
Right. Because to us it's text. It makes sense. It's logical.
Yeah.
But to the computer, to the CPU, it's just
Yeah.
characters. Gibberish, basically. It needs this profound transformation to become actual instructions the machine can understand.
Okay, so it needs translating.
Exactly. And it helps to think of compilation not as one single magic step, but more like an assembly line, a multi-stage pipeline.
A pipeline, I like that. Okay.
Yeah, your source code goes in one end, and it goes through this sequence of really precise operations. Each step does something specific, transforming it bit by bit until pop, out comes the executable at the other end.
Okay, pipeline analogy. Let's walk down the line. What's station number one?
It all kicks off with preprocessing. This is where a tool scans your code, specifically looking for lines starting with that hash symbol, the hashtag.
Ah, like hashtag include.
Exactly. Hashtag include directives literally get replaced by the contents of the header files. It's like pasting them right in.
Okay.
And hashtag define macros get expanded, comments get stripped out, and those conditional blocks like hashtag ifdef are processed.
So it cleans things up and pulls everything together.
Pretty much. The output is one single, often massive translation unit. Basically one giant C++ file that's ready for the actual compiler. Got it. So all those includes and header guards, that's handled before the real compilation even starts, like prepping the ingredients, kind of.
Ricely, preparing the raw materials.
Yeah.
Then this big file moves to the next stage, the compilation phase itself. And this is really the heart of the compiler's work.
Okay, the main event.
Yeah, and it happens in a couple of steps. First is lexical analysis, or lexing. Your code gets broken down into tiny pieces called tokens.
Token?
Think of them like the individual words and punctuation marks of C++ on. Keywords like int or class, your variable names, operators like plus on, semicolons, all become tokens.
Okay, breaking it into words.
Then comes syntax analysis or parsing. This is where the compiler checks if the sequence of tokens follows the rules of C++ grammar.
Like sentence structure.
Exactly. Does it make grammatical sense? It builds this structure called an abstract syntax tree, or AST. Think of it like a family tree for your code, showing how everything relates.
And if you mess up the grammar, like forget a semicolon.
This is where it catches it. The parser will complain right here if the syntax is broken.
Okay, so checking spelling and grammar, building a map of the code, what's next?
After parsing, we get into semantic analysis. This goes deeper. It's not just about grammar, but about meaning.
Meaning.
Yeah, does the code actually make sense according to C++ rules?
Yeah.
This is where it checks type compatibility. Making sure you're not trying to add a number to a text string, for example.
Right.
And it verifies that you declared variables before using them. It really relies on the compiler's deep understanding of the C++ standard here. It's ensuring your code is logically sound, not just grammatically correct.
That's a ton of checking. But crucial, I guess. So once the compiler understands what we wrote and that it makes sense, does it finally make machine code?
Almost. But first comes optimization. And honestly, this is where a lot of the perceived magic happens.
Ah, the secret sauce.
Kind of. The compiler takes this internal representation it built, based on the AST, and looks for clever ways to make the code run faster, or use less memory, or just be smaller overall, and crucially, without changing what it actually does.
How does it do that?
Oh, lots of ways.
Yeah.
It might inline functions, basically pasting the function's code directly where it's called. It might unroll loops, reorder instructions so the CPU can execute them more efficiently, get rid of calculations that aren't needed.
Wow.
Yeah, the quality of a compiler's optimizer makes a huge difference in the final runtime performance. It's like having a super smart performance engineer constantly reviewing and tweaking your code.
So it's not just translating, it's actively improving our code, maybe even finding efficiencies I didn't spot.
Absolutely. A good optimizer can spot patterns and speed up opportunities that are really hard for a human to see sometimes.
Okay, so after optimization.
Then we get to assembly and code generation. The compiler translates that optimized intermediate code into low-level assembly language. That's specific to the target processor architecture, like by 86 or ARM.
Okay, closer to the metal.
Right. Then a separate tool called an assembler turns that assembly code into pure binary machine code, the zeros and ones, and saves it in what's called an object file. Usually ends in .od or .onj.
Object files, right. With multiple object files.
Exactly. And they don't just combine themselves. That's the job of the final stage. The linker.
Ah, the linker, okay.
The linker takes all your project's object files, plus any static libraries you're using, and combines them into the final single executable file. Its main job is resolving references between those files.
Like if main.cpp calls a function that lives in utils.ctp.
Precisely. The linker finds the machine code for that function in utils.obj and connects the call from main.obj to it. It stitches everything together.
Okay, wait. Is this where that awful unresolved external symbol error comes from? Because I have definitely pulled my hair out over those.
Bingo. That's the one. It's super common, super frustrating.
But when you understand this pipeline...
That it clicks. The compiler did its job on each file individually. The syntax was fine, the types checked out, but the linker, when trying to connect everything at the end, couldn't find the actual compiled code for some function or variable that was declared but never actually defined anywhere.
So it's not a compiler error, it's a connection error, a logistical problem.
Exactly. You're missing a piece or you forgot to link against a library. It turns this cryptic message from, like, compiler witchcraft into a solvable puzzle. Where's the definition? Understand the stages makes even those errors way less intimidating.
That's a huge clarification, honestly. And it really underscores how complex C++ is. Things like templates, metaprogramming, constexpr, they must put incredible demands on these compilers.
Oh, absolutely. That's why building and maintaining a modern C++ compiler is such a massive, resource-intensive effort.
Okay, makes sense. So we get why we need them and kind of how they work now. Let's talk about the actual tools. Who are the main players, the titans?
Right, the titans of translation. Well, first, you've got the cornerstone, the veteran, GCC, the GNU compiler collection.
Ah, good old GCC.
Yeah. Its history goes way back to Richard Stallman and the free software movement in, 1987? It was foundational for GNU Linux. Its whole philosophy is about freedom, collaboration, open source.
Still the default on most Linux distros.
Pretty much everywhere in the Unix-like world, yeah.
Yeah.
It has a more, let's say, traditional architecture, kind of monolithic. It has front ends for lots of languages, C, C++, ARI, Fortran, Ada, Go.
Wow, okay.
And they all feed into shared optimization passes and backends. Its real strength is that ubiquity, that robustness.
Yeah.
Decades of refinement. It supports a massive range of platforms. And it's often, pushing the boundaries, implementing new C++ features very early. It's the workhorse.
Okay, the reliable workhorse. So who's challenging the champ?
That would definitely be Clang and LLVM. The modern challenger, you could say.
Right. I hear about Clang a lot, especially with editor tools.
Exactly. Clang started at Apple around 2007. They needed something faster, more memory efficient, better for IDE integration, and crucially, with a more permissive license than GCC's GPL.
Ah, the licensing aspect.
Yeah. So they built Clang as a new C-family front end, specifically designed to work with LLVM, which is the backend optimizer and code generator.
And the architecture is different.
Totally different philosophy. Clang isn't just one program. It's designed as a set of reusable libraries.
Yeah.
That modularity is key. It's why there's this whole ecosystem of tools built on Clang. Clang Tidy for static analysis, Clang Format for code style, Clang for language servers and IDEs.
That makes sense why it integrates so well.
Yeah, and LLVM itself is this powerful infrastructure. It's so successful that even Intel, as we'll see, rebuilt their latest compiler on top of Clang LLVM. That says a lot.
And the license.
It's the Apache 2.0 license with LLVM exceptions. Very permissive. It doesn't force you to open source your changes to the compiler itself, which is why big companies like Apple, Google, Microsoft, Sony, Intel have all heavily invested in it. It's also why new languages like Swift and Rust chose LLVM as their foundation.
Okay. So for a developer, what's the big draw of Clang?
Developer experience, hands down. Especially the error messages. Remember those horrible template errors that look like Klingon?
Oh, don't remind me.
Clang really pioneered making those understandable. Clear, color-coded messages, little arrows pointing to the exact problem, sometimes even suggestions on how to fix it. It just makes debugging way less painful. Plus, it's generally known for faster compilation and lower memory use.
Faster builds and better errors. Sounds pretty good. Okay, who's next?
Next up, the Windows native. Microsoft Visual C plus C or MSVC.
Right. If you're doing Windows Dev, you're probably using this.
Almost certainly. It has a long history, deeply integrated with Visual Studio. Its whole reason for being is to provide the absolute best, most seamless experience for building Windows applications.
Makes sense. Is it architecturally different again?
Yeah, it's proprietary, closed source, tightly coupled with the Visual Studio IDE, its debugger, its own C++ standard library implementation. The works. One distinct thing is its use of redistributable runtime libraries, those DLLs you often need to install with Windows apps.
The Visual C plus redistributable packages. Okay.
Exactly. Its main strength is that tight integration. The Visual Studio Debugger is widely considered world-class. It has first-class support for all the Windows APIs like WinAPI, DirectX, and critically, most third-party Windows libraries are built and tested with MSVC, so compatibility is usually smoother.
So the default choice for Windows, pretty much.
Definitely the dominant one.
Okay, that brings us to the fourth titan. Intel's C++ compilers, ICS now, right? Not ICC.
Right, big shift there. For years, ICC, the Intel C++ compiler, was the name for squeezing every last drop of performance out of Intel CPUs, especially in high-performance computing scientific stuff.
Yeah, I remember hearing about that.
But Intel made a strategic move. They've largely deprecated the classic ICC and introduced the new ICX compiler. And guess what it's built on?
Let me guess. Clang and LLVM.
You got it. It uses the Clang front end and the LLVM back-end infrastructure. But Intel adds their own secret sauce proprietary optimization passes, code generation specifically tuned for the latest Intel hardware features, like advanced vector instructions.
So it's like Clang LLVM, but with extra Intel performance tuning.
That's a good way to put it. It's a hybrid approach. And a big plus, it's now free, part of their One API toolkit.
Oh, really? That's huge.
Yeah, makes those advanced optimizations much more accessible. And ICX is really pushing heterogeneous computing with this thing called DPC++ SYCL.
Okay, what's that?
It's basically an extension to C++ that lets you write code that can run efficiently across different types of processors, CPUs, GPUs, even FPGAs, all from a single source code base. It's designed for these really complex, demanding workloads.
Wow, so targeting specialized hardware from C++.
Exactly. So think high-performance computing, HPC, scientific research, financial modeling. That's where ICX shines. Plus, it integrates tightly with Intel's own optimized libraries, like TBB for parallelism and MKL for math routines.
Okay, 4 major players. GCC, Clang LLVM, MSVC, ICX. So how do you choose? You said there's no single best one.
Exactly.
Yeah.
It's never about which is best overall. It's always which is best for this specific task I'm doing right now. You fit the tool to the job.
Okay, so what are the key things to think about when making that choice?
Okay, first big one, C++ standards compliance. The language keeps evolving, C++ 17, C++ 20, C++ 23. Using a compiler that supports the latest features you need is obviously critical.
Yeah, you want those new goodies. How do they compare?
Well, historically, GCC was often the first out of the gate with experimental implementations of new features. But honestly, these days, GCC, Clang, and MSVC are all pretty quick to adopt new standards. They're all racing to support C++ 20 and C++ 23 features. ICX benefits from Clang's compliance too. The best bet is always to check a specific feature status on a site like cppreference.com for the compiler version you're considering.
Good tip. Okay, what else? Performance, obviously.
Right, performance. But that breaks down a bit. First, there's compilation speed. How long does it take to actually build your code?
Yeah, nobody likes waiting hours for a build.
Exactly. Clang often gets cited as being faster and using less memory than GCC, especially on large projects, though GCC has made big strides. But MSVC within Visual Studio has really excellent incremental build times. It's very fast at only recompiling what changed.
Ah, that's a big productivity win.
Definitely. And ICX, being LLVM based, generally has good compile times too.
Okay, compile speed. Then there's the big one, runtime performance. How fast does the final program run?
Yeah, this is where it gets really competitive and honestly complicated. GCC and Clang are constantly leapfrogging each other in benchmarks. One might be faster for certain types of code on one release, the other pulls ahead on the next. There's rarely a clear universal winner for general code. Intel's ICX, and ICC before it, traditionally had an edge for very specific, computationally heavy scientific workloads on Intel hardware, especially with things like auto-vectorization. But even that's not guaranteed across the board.
So it depends.
It totally depends. The only reliable way to know which compiler produces the fastest code for your specific application on your target hardware is to benchmark it. Measure it yourself, period.
Okay, benchmark, benchmark, benchmark. Got it. What about the size of the executable? Does that matter?
It can. Binary size is crucial for embedded systems, IoT devices, or anything where space is tight. Clang often has a reputation for producing smaller executables out of the box. GCC can be tuned for size with flags like me shows. It's always a trade-off, though optimizing purely for size might make the code slightly slower and vice versa.
Right, trade-offs. Okay, beyond performance, what about just using the thing, the developer experience?
Hugely important for day-to-day sanity. First up, error messages. We touched on this.
Clang's clear messages.
Clang really raised the bar there. Those expressive diagnostics, color, pointers, fix-it hints were a game changer. But to be fair, GCC saw that and improved dramatically. Its errors are much better now. MSVC's diagnostics within Visual Studio are also very good.
And C++20 concepts help too, right? Making template errors less scary.
Oh, absolutely. Concepts were a massive improvement for clarifying template errors across all modern compilers that support them.
Okay, errors. What about debugging?
Essential. Debugger integration. GCC typically pairs with GDB, the GNU debugger. Standard on Linux, very powerful, maybe a bit of a learning curve.
Right.
Clang pairs with LLDB, the LLVM debugger.
Yeah.
Default on macOS, also very powerful. And MSVC integrates seamlessly with the Visual Studio debugger, which many people feel is one of the best debuggers available, period.
Can you use, say, GDB with Clang code?
Often, yes. On Linux and macOS, GCC and Clang usually use a standard debug info format called dwarf. This lets debuggers understand the code structure. MSVC uses its own proprietary PDB format, so the Visual Studio debugger works best with MSVC compiled code.
Okay. And how do build systems handle all these different compilers, like CMake?
Yeah, build system integration is key. Luckily, tools like CMake and Ninja are pretty much the cross-platform standards now. They're designed to work smoothly with GCC, Clang, MSVC, ICX, you name it.
So you can switch compilers easily in your CMake file.
Mostly, yeah. CMake handles generating the right build files, like make files or Ninja files, for the compiler you choose. Ninja then calls the compiler with the right flags. It makes cross-platform development and compiler testing much easier.
That's great. Okay, any other big factors?
Well, the target platform is often the very first filter, building a native Windows app. MSVC is the path of least resistance. Targeting Linux, macOS, or aiming for cross-platform. GCC and Clang are your main choices. Doing heavy compute on Intel hardware. ICX is worth investigating.
Makes sense. And licensing. Does that often impact the choice?
Sometimes, but maybe less often than people think for just using the compiler. If you plan to modify the compiler itself or distribute it as part of a product, then Clang's permissive Apache license is less restrictive than GCC's copyleft GPL. But if you're just using the compiler to build your own closed source or open source application, both GCC and Clang are generally fine. You can ship apps built with either without issue.
Okay, good clarification. So those are the main titans. Are there others?
Oh yeah, definitely. There are more specialized compilers, especially for things like embedded systems, microcontrollers, what they call freestanding environments. You see names like Keel MDK, MPLAB XC for Microchip, TI's ARM Clang compiler.
Right, for specific hardware.
Exactly. And what's interesting is that many of these vendors are also increasingly adopting LLVM infrastructure, building their specialized compilers on top of Clang LLVM. It's really becoming a foundational technology.
Wow, LLVM is everywhere.
It really is spreading.
Okay, this is maybe a bit niche, but I've seen these websites where you can type code and see the assembly.
Ah, yes. The online compiler explorers. These are fantastic tools, especially for learning. You're probably thinking of Matt Godbolt's Compiler Explorer.
That's the one. Godbolt, yeah.
It's an incredible resource.
Yeah.
You type C++ code, and it instantly shows you the assembly output generated by dozens of different compilers and versions, side by side if you want.
Live as you type.
Live, you change your code, the assembly updates. It's amazing for understanding exactly how a compiler optimizes your code, comparing different compilers, learning how C++ features translate to machine code, even debugging tricky performance issues by looking at the raw instructions.
That sounds like a superpower for understanding compilers.
It really is. And there are others too, like Wanbox for just trying snippets on different compilers, Kaleru for runnable examples, QuickBench for quick performance micro benchmarks, CP Insights, which tries to show you what the compiler does implicitly. These tools have like democratized compiler exploration. Anyone can play with this stuff now.
Fantastic resources. Okay, wow. We've covered a ton of ground here.
We really have.
Hopefully it's clearer now that choosing a C++ compiler isn't about finding that one best tool. It's really about matching the compiler's strengths to what your project actually needs.
Exactly. So just to quickly recap the big four: GCC, Think Reliable, cross-platform, the open source standard bearer, great for portability, stability, especially strong on Linux. Clang, LLVM, modern, fast compiles, developer-friendly, great diagnostics, amazing tooling ecosystem. Choose it for speed, error messages, and that rich tool integration. MSVC, the Windows native champion. Integrated, powerful debugger, seamless Visual Studio experience, the go-to for Windows development. ICX, the performance specialist from Intel. Now LLVM-based, free, great for HPC, scientific computing, getting the most out of Intel hardware, and exploring DPC++ SYCL.
That's a great summary. And this whole landscape, it's not static, right? It keeps changing. What does the future look like?
Yeah, it's constantly evolving. We're definitely seeing the rise of LLVM continue. Its modular design is proving really successful as a foundation. There's also a huge focus on the broader tooling ecosystem around compilers, better build systems, dependency management, static analysis tools, formatters.
Making the whole development process smoother.
Right. And then there's a really exciting, maybe slightly unknown impact of AI.
Yeah.
People are exploring how AI could lead to even smarter compiler optimizations, maybe automated bug detection, perhaps even AI assisting with code generation or completion right within the compiler or IDE.
Wow, AI optimizing our optimizers. That's pretty meta.
It is. The whole journey of the C++ compiler kind of mirrors the language itself, doesn't it? Always adapting, getting more complex, but hopefully always improving.
Definitely. So after peeling back the layers on compilers today, what stands out most to you listening in? Did anything surprise you? And looking ahead, how do you think AI might change how we interact with these tools, or maybe even how we program in the next few years?
Yeah, fascinating questions to ponder.
Let us know your thoughts. Keep exploring, keep building, and thanks for diving deep with us today.